Hello and welcome to the 22nd episode of Current Affairs. This is the first English one we are producing, and if you like this format, please let us know. Today, Dr. Tanuj Hasija talks to Professor Dr. Sina Saravi about his research in modeling and design of photonic quantum systems.
Yeah, welcome back to our podcast, Current Affairs. And my name is Tanuj Hasija. I am working as an academician rat in Signal and System Theory group in Department of Electrical Engineering. And it's my first podcast, and it's also it's for our first English podcast, as we have got a lot of requests from the students to also have some podcasts in English. And with me, I'm honored to have Professor Dr. Sina Saravi. He leads the research group Modeling and Design of Photonic Quantum Systems in our university. And the idea is that we'll take you into what Professor Saravi's work, maybe also talking about light, quantum physics, and how it all connects to electrical engineering. And it's an honor to have you here.
Thank you very much. Thanks. I'm also excited to be here. I never did a podcast before, so, let's see how it goes.
Okay, that's great to hear. So I'll start with a bit of a warm-up, either and or questions, to get us started. And you have to say whatever first thing comes to your mind.
Interesting.
Okay, so are you ready, Professor Saravi?
Yes. Now I'm scared.
Okay, coffee or tea during research days?
Oh, coffee, obviously.
Paper and pen or digital notes?
Depends. If I'm by the sea trying to read a paper, then I prefer paper. But usually, tablet is probably easier.
Mm-hmm. Lab experiments or computer simulations?
Hard question. I rather doing calculations analytical on a paper. This is my favorite thing to do. But now that I'm a bit older, at least I prefer sitting down and doing simulation. I mean, lab work is hard work. You have to stand up all the time.
That is indeed true. Yeah. Physics or mathematics? What's more fun?
Physics, definitely. No offense to our math colleagues, obviously, because I remember starting in high school a bit more in the direction of math, because we had these student Olympiads, which I think they also have in many countries. And there I started with math, and I think I failed really for various reasons, but I was doing better at physics, so I like physics more.
Of course, those are interconnected to a certain extent, but every one of us has always a favorite one, right? Yeah. Quantum computers, do you think next big revolution or overhyped?
I mean, I think the next big revolution will be some type of computing system. Now, the quantum aspect, I think, would also be an important part of it. Now, if it would be fully quantum, I don't know. But I would say that's the hype is in the right direction.
Mm-hmm. Okay. The last but not the least, and maybe that would also relate to some of our students, are you strictly structured or creatively chaotic?
Probably the second one, at least. Not very well structured in that sense. I have millions of folders on my computer, which I can only find. Yeah, so the second one.
Yeah. I can also relate to that. Lots of tabs, lots of open-ended questions.
Yes, lots of tabs indeed.
Okay, then I guess that was our warm-up a bit to start with, and we'll go with the theme of getting to know you now, a little bit about your background and motivation before we dive into our research. So, how did you get into electrical engineering and especially photonics? And when you said that, okay, that's it, how did you get to where that's what I really want to do? And maybe also about your background, into this particular field.
Yeah, well, as I said, interestingly, I mean, in high school, I was very much into physics. And then, it's a story that I always tell to friends that, I was between choosing electrical engineering and physics. And my father, who is also a university professor and is a math professor, he has a friend who did his bachelor in electrical engineering, then became a very hardcore theoretical physicist. And he advised me to start studying by electrical engineering and not physics. And his reasoning was that, well, if you want to get to know the real world and sort of, have a feeling for real numbers, go with the engineering. And I took that advice, and I think it was a good advice. So that's how I started on electrical engineering, which I did my bachelor in Iran. And this was with the specialization of telecommunications. So this was already a bit more focused on fields and waves and Maxwell equation and these type of things. And then, I came to Germany for my master's studies, which was Master of Photonics in Jena, Abbey School of Photonics. And then I did my PhD in physics, also in Jena. And this was more on the topic of, photon pair generation, nonlinear optics. So there, the quantum part was really in my doctoral studies.
Mm-hmm. And so you mentioned that you're originally from Iran, and for how long have you been in Germany, and how do you find Germany?
So I was until the end of my bachelor in Iran, probably 22, as in when I was 22, I moved to Germany, and then I was all the time in Germany, in Jena, where I did my master and doctoral studies, and also my postdoc, and started my junior group also in Jena and in Friedrich Schiller University. And then I came to Paderborn from last year. So even all my time in Germany, I was in Jena. I was pretty happy in Germany. I liked them, and that's why I stayed. So I was also happy with Jena. I'm also happy with Paderborn. When I usually was staying in the smaller university student populated city, which I always liked the atmosphere, and it's nice.
Mm-hmm.
Could be a little bit sunnier, but that's fine.
That indeed is true. I originally come from India and New Delhi, and definitely it's a different feeling. Especially a small town like Paderborn. But so how do you feel and see Paderborn as a city? And you mentioned that you have been there since last year. So and how are your first few impressions?
I would say it's very good. Not just the university, but also the city overall, because I had to, when you move to a new city, you have to go to a lot of city offices and do a lot of different administrative things, both at the university and the city. And my impression was very good. People were very friendly, very, very helpful, both at the university and outside. So overall, my first impression was very good. And also the city, I would say Paderborn, for its size, where you expect it to be a small city, it's actually, has quite won't call it a big city feeling, but it has a lot of, I don't know what's the right word, it has a lot of options. Yeah, so overall, I'm pretty happy with Paderborn.
That's good to know. And maybe the last question about this theme would be, based on your experience in Germany as first an international student, then a doctoral student and a postdoc, and gradually moving into research, especially to our international audience and students, what kind of advice would you like to give them, especially those who are new into the system?
Well, I can give them a lot of advice depending on which stage of their career they're in. But if it's really about the incoming international students, which usually I guess they are, either at the master level or the doctoral level, the first couple of months usually is the hardest, I would say, because, academically, and until you get sort of used to the system. For example, when I was a master's student, until I get used to the classes and the way the classes are held and the way I have to do whatever homework, also the system, when you get used to it, especially, in Germany, there is a lot of, usually more than what I was used to in terms of paperwork. But these are the things that one would take some time to get used to it. So usually I would guess, at least for me, maybe the first few months, at least academically, was the hardest until I sort of get settled into the environment, into the system. But once this stage is over, which I would say there are a lot of people also there to help you, also at the university. So you sort of get settled. Once that stage is over, well, it's more smooth sailing. So at least, well, I don't know. My advice is once you come, well, hold through the first couple of months where things are a bit different than usual. But after that, well, it's more smooth sailing.
Thank you for a great piece of advice. Yeah, I agree. I mean, so to all our international students as well, I mean, just for the first few months, stick around, and those would be probably the most challenging, and then it should ease out, and ask for help if you need it. Maybe talking to you about a little bit about your research and your group in general as well. I mean, about photonic quantum systems, what they are to somebody like a very early bachelor students or somebody who's starting electrical engineering. How would you describe these things? Because it's overall, it's a fascinating topic, as you said. I mean, maybe could be the next big thing, and we hear a lot about quantum systems, quantum computers. Multiple players are investing into those. A lot of money into it, and what is it in very general terms? What it is about, and how are different from regular computing systems, and where do you see this field going?
Good question. I mean, well, it's probably quite easy to make a mistake in trying to explain the physics, because when you try to give a very general explanation, you have to be very good at knowing that topic, so you don't oversimplify it. But I mean, to put it in simple terms, it's a new paradigm for information processing compared to what we usually have, which is digital information processing, right? Where you have usual computers where the information comes in bits, zeros and ones, and this is the dominating form of information processing computation that we have. Quantum computing, and among that, photonic quantum computing, because it's also a larger category. It's not just photonic who is a contender. I mean, it's a strong contender in the race. I'm biased towards that, but nonetheless, there are other forms of also quantum computing systems. But all of these, I would say, fall under the category of analog computing in a sense. So you're not working necessarily with zeros and ones of the digital world of electronics, but you're working with signals of physical systems in an analog form, where in the photonic world, this would be, well, light, essentially. And adding to that, the quantum aspect is, well, in addition to this analog computing with light, you're trying to also make use of the quantum properties of light. So the famous quantum properties that we might know is superposition, where, well, the Schrödinger cat could be dead or alive. So the photon could be here or there. It could have this polarization or that polarization, this frequency or that frequency. So this would be the superposition principle. And it could also have, entanglement, which is a quantum property, where if you find one photon in a certain state, where it could be in, well, I don't know, this or that polarization, by measuring that photon in a certain polarization, you would know that your other photon somewhere far away would instantly collapse into a certain state. So this is sort of the spooky action in the distance that one might hear. So the superposition and entanglement is then the fundamental quantum properties that you try to explore for your specific information processing application. For example, if you're trying to do quantum communication, well, you could use these principles to make your communication channel fundamentally unhackable, in a very simply said. And on the side of computing, well, you would try to use these principles to make your computation exponentially faster. I mean, there are a lot of caveats to it. There are a lot of, it's not as simple as I said, and that's why so many people are working on it. But just very simply said, that's the story.
Yeah, it's pretty interesting. I mean, we were in the analog world, or we live in the analog world, and then using computers since last 50 to 100 years, we have moved into the digital world, right, with zeros and ones and bits and quantization. And is it fair to say then, are we going back to the analog world in terms of computation, or do you see it somewhat of a mixture of staying with the digital world and combining the advantages we get from the analog world?
That's a very good question. I mean, getting a bit maybe technical in it, what the advantage that the digital world has is it's very good at being precise and correcting your errors. Whereas the analog world comes with a lot of advantages in computation, especially, I mean, it could give you possibility of doing things with lower energy consumption. I mean, if you do it correctly, and you could also have very much higher computational capacity, especially if you use the quantum principles. But then the disadvantage, which is I would say one of the main differences to digital, is that you now are more prone to errors, because now you're not working with nice zeros and one signals, but now your signals are, a continuous range, for example, of numbers, and then you could be more prone to errors. I mean, there are obviously also schemes against these things, but then what you want to do is, exactly as you said, use probably a combination of these things, or use them in the right place, right? So if you want to do financing on your Excel table, you probably don't want to use the quantum computer for doing this. I mean, it would be overkill for that task. But I mean, you already have computers that do this very well for you, and also, they are not prone to errors for that. But then, if you want to do a very specific, computationally heavy task, like a simulation of some kind, or for example, nowadays, this is also becoming an important topic if you want to do some type of AI type calculation, sometimes called neuromorphic calculations. These are the type of things that you could hopefully benefit from by using an analog photonic system, which could be classical, but it could also be quantum. And that's where you could potentially get advantages. But the main thing is, you're not trying to substitute a regular computer and all its functionalities with an analog system. That's not what they are for, and nobody's trying to do that.
Okay, quite interesting and fascinating. And before we go on to, let's say, the difference between a regular, or not a regular, but a quantum computer in general, how a layman knows, versus a photonic quantum system, just getting back to one of the points that you talked about, AI, which is a big theme right now, especially now we know with all these LLMs and ChatGPTs and other tools as well, that is or would change our workings, especially at a research, but also in other fields as well on a day-to-day basis. Now, how much it affects, we'll see, and time will tell. But it would have some sort of an effect, and it is there. It's not going anywhere now. And you talked about that it could be integrated. How or do you see a future with AI systems, with quantum computers being integrated to even benefit us more?
Sure.
Or are we talking about this kind of a very, state of having even more power to the AI system with quantum computing, and especially with consciousness and other kind of, dangers that some of us have?
Sure. I mean, there are a lot of special scenarios where things could go terribly wrong, but at least as a scientist, that would mean we are already reached the peak of the mountain of success with our. So in some sense, that means our job is done. But maybe then it's bad news for everybody else. But yeah, hopefully we're not going to get there with the quantum AI taking over. But in some aspect, I think the AI topic is also a strong motivation. Or an added motivation for the drive for, at least from my perspective, for this quantum computing business, because the AI is now demanding so much computational power, which at the same time also demands a lot of, energy consumption. I mean, that's also getting to be one of the big problems for AI. So it's really driving the research nowadays, where people try to find new solutions to implement these type of, AI-based computation, because it's a new category of computation that is, eating up all the resources. And this is now driving this research on what's called neuromorphic physical hardware. So again, not just photonic, but a larger category of physical systems that could, in an analog way, essentially implement the calculation for the AI. I mean, at the end of the day, the AI, for example, represented by a neural network that you hear a lot, at the end, it's a computational task. I mean, you give it input, there's a function that acts on it, and you get an output. So, and people are trying to, implement this instead of doing it on a digital computer or a GPU. They try to find a physical system that can do it in an analog way, faster or more power efficient. And again, photonic is a strong contender in that race. And I would say it also drives the motivation for quantum photonic information processing, because, the quantum is sort of, the extra add-on to the analog computing world, because now you can also use the quantum principles, which give you new tools and capabilities. So I see that as an extra motivation for this field of photonic computing and photonic quantum computing.
Thank you for clearing that. Okay, then, maybe let's talk about how are photonic quantum systems different. I mean, you talked about some of the aspects that it takes the properties of light into account, and also, integrates that with the quantum principles. How would you say these are, both in application and theory, different from the quantum computers? For example, the ones I know are, really have to be put at or cooled down at, very, very low temperatures to have those principles into place.
Among these different systems, there are different physical systems that you can use. Essentially anything physical is living in a quantum world, right? So everything is governed by, quantum physics principle, in a sense, at least where in our world on Earth, where things are not going maybe too much at relativistic speeds, or, we are not in the middle of a black hole where all the laws change. At least around us, everything is working nicely with quantum principles, which means you can, in principle, maybe use anything.
Yeah, I hope not in simulations. We are not in a black hole, or
Yeah. So aside from those scenarios, then at the end of the day, it's a question of which physical system you can control well at those quantum levels, where you can preserve quantum information, where it's not sort of being disturbed by interaction with the environment, because quantum information is very delicate in a sense. And there are different candidates for doing this. Not trying to give an overview on this, but the type of systems that you have to cool are usually, anything based on solid state systems or atomic systems. And usually then you have to cool these systems because you're trying to keep the quantum information in the state of these atoms, for example. And these could be easily disturbed if these atoms are, interacting with an environment that is then disturbing its quantum information. I mean, they're not just cooled, they're also in vacuum, so you have to do a lot of things. It comes with its disadvantages, but for sure it also comes with its advantages, in the sense that, with atoms you can also control them and maybe implement quantum gates in a more standard way. And I'm for no way an expert in that, so maybe I also say things the wrong way there, but at least that's my impression. Now with photons, there are advantages to it. The advantages is you can transmit quantum information with photons at room temperature. They're quite resilient in some senses to disturbance compared to other type of systems. So this is really a big advantage of photonic systems. One other big advantage is that, you can encode a lot of information on light. I mean, nowadays, our whole internet is essentially based on, communication in fiber optical systems, right? And that's why you can really encode a lot of information on photons. So this is a very good point for them, and this is motivating a lot of researchers also. So there are a little bit easier to work with. I mean, you can use integrated photonics, for example, which is also something that we are. So it's strongly pursued at the Paderborn University in the Fox Institute, for example. And there, well, these technologies are quite advanced because of the maturity of semiconductor technology, which sort of, in a sense, well, all these computers or mobile phones that we have, I mean, these are all the very mature nanofabrication technology that exists for these chips, and these have, in a way, also resulted in the maturity of photonic integrated systems, which we can use these type of technology. So the technology also is quite advanced in that sense. The only disadvantage, or maybe the biggest disadvantage of photons is, well, coming from their advantage, actually. So the fact that they are very resilient comes from the fact that they don't easily interact maybe with each other, which is good. So that means you don't have crosstalk between photons, but at the same time, it also makes it very hard to implement things like, well, logic gates in a sense, or gates that one photon affects the property of another single photon. Because, well, the photons are so good at not interacting with each other. But, well, I mean, that's a part where a lot of people are trying to work on and find solutions on how to use, for example, nonlinear optics to make the photons interact with each other, or use some mediators like quantum dots maybe to help the photons interact with each other, or come up with a whole different paradigm in computing where instead of doing gates where the photons have to interact with each other, do something which is called one-way quantum computing, where you sort of prepare your large entangled photonic quantum state at the beginning, and they just go through a set of maybe directional couplers or beam splitters. They sort of do linear interaction with each other, and then you just measure them at the end. So this is a different type of paradigm where you don't need maybe gates, but it has its own challenges. Then you have to come up with advanced sources of quantum light that can generate these high, what's called cluster states, for example. So in that sense, there is a lot of, well, people working on many different aspects of this. I mean, I myself am working, for example, more on this sources of quantum light, trying to improve these sources. A lot of people also in Paderborn, for example, are working not just on the sources, which they do, they also work on the other end of it, which is detection of quantum light. People also work in the middle to manipulate quantum light. Yeah, so there is a lot of interesting research, and I would say the research is also quite advanced. There are also companies on the topic of photonic quantum computing.
So are there prototypes? I mean, I've heard about, not mentioning, let's say, the names of companies, but there definitely is a big quantum computer that a lot of big companies and big tech companies are developing. Is it also similar for the photonic quantum systems and photonic quantum computers?
Maybe I'm not up to date, so I'm not sure if there are prototypes or not. Maybe there is that I don't know, but I can at least mention that, I mean, in Paderborn and Fox Institute, there was also a prototype of a photonic quantum computer. Again, well, since myself, I'm new to Paderborn, maybe I don't know all the details, but at least there is also a prototype there was a realization of a prototype for a photonic quantum computing system. If it's a full quantum computer or not, well, probably not at this moment, but there is at least a system that can do some type of photonic quantum computing, which is, I would say, if I don't say it wrongly, I think it's the first of its kind in Germany at least. But I refer people to the Fox Institute's website for more information.
Yeah, it's definitely. Thank you. I mean, it's really a growing field, and especially also at Paderborn with the Fox Institute opening as well. And yeah, for all the new interested students, and even for, people who are interested in these kind of topics, I mean, stay tuned where this is going. And I think I read that soon, by the end of February, we also have a grand opening of the Fox Institute. So feel free for everyone who's listening to this podcast to attend. And are you attending that,
Yes, you also have to register for it.
Okay, then thank you for
Feel
that.
free to register for it, but I think you can find it on the website of the Fox Institute. I don't know when the deadline is. I mean, I think there's two parts to the event. There is like a general part which has rather general talks from different people, but there's also a scientific symposium which is in the evening. I think one can register for them both or separately. Well, at least I think the registration link is publicly available on the website.
Yeah, so it's whosoever is interested to know more about these, and maybe we also see the prototype of, maybe I'll also try to register and see something nice about there as well. Okay, so then let's dive a little bit deeper into what you are doing with. You briefly mentioned about you're working with the sources of the light itself. I mean, how that could be used. And the name of your research group is Modeling and Design of Photonic Quantum Systems. It sounds very technical, very futuristic as well. But if you had to explain it to someone, someone to the new students, new bachelor students, or even at a master levels, not familiar with this, how would you say what you do?
I would say that, well, first, generally speaking, I'm more on the hardware side of this photonic quantum technologies, because I mean there is really a wide field of research where people are working on the algorithms, essentially how or what type of protocols or what type of computing algorithm can I implement using quantum light, and this is its own field of research. I am more on the hardware side, which is, well, the category of people who are trying to realize components or systems for this photonic quantum computing. I mean, again, in that, it's a large category. We zoom more to find me, and I'm more on the side of trying to realize, well, sources of quantum light, or at least, well, I am more on the theory and design side, but I also have some experimental activities in that category. But this is, well, really, if you consider a quantum system, separating it in three big parts. Well, first you have to generate quantum light, then you have to manipulate quantum light, then you have to detect quantum light. So in some sense, I'm sitting on the, well, first part of this pipeline. And they're a bit more specific. My focus is trying to, well, on one side, see how one can use nanophotonic technology to realize these sources in a way that they are, well, more functional, because, I mean, nanophotonic gives you now a lot of options. It's not just about making things more compact, which, well, obviously you want to do, but also, well, nanostructuring technology would allow you to really make photonic structures with interesting functionalities where, well, light would behave in a certain way, which you might not be necessarily able to achieve if you have a large component which has, well, a large structure and not these fine features in it. And this is what I try to do, try to use essentially nanophotonic for designing novel components for photonic quantum technologies. And a bit also on a more general level, I also try to come up with, well, new ways of realizing components which are a bit different than the usual ones. I mean, we have more established technologies, which a lot of them are good in certain aspects. They have their own, well, disadvantages. Some other technologies, for example, in sources of quantum light, well, different categories of sources do different things better than each other. And I'm trying to sort of come up with maybe new solutions, possibly, well, hybrid ones where you put things together, where you can sort of overcome the disadvantages while keeping the advantages of these technologies. So there, my work is a bit more abstract.
Okay, interesting. Yeah, let's talk about something that's also especially relevant to our listeners. So what do you offer to the students at your group? So could be which kind of courses or lectures do you teach? Maybe student projects or lab work or seminars that you offer, or could also be around what kind of thesis that you offer, more theoreticals or hand-ons?
For the past 2 semesters, so I mean, I'm new obviously here, and I'm a little bit I have to a little bit probe the environment and the students just to see, well, also what are the interests and what are the background of the students, such that my courses and offers are useful for students. What I offered, at least in the past 2 semesters, was 2 lectures and a seminar and a project. I mean, the lecture was, one of them was on fundamental of optics, where it's sort of a more special take on the course Field and Waves, which deals with Maxwell equation, but this goes a bit more specific to the direction of optics and photonics, and try to study concepts like diffraction of light, dispersion of light, these type of topics, where as an optics or photonic guys, you need to know. If you also want to work in my field of research, well, that's something that you probably need to know. The other course that I offered, which might be a bit more advanced, but, again, I'm trying to feel the environment, is an advanced quantum optic, which is quite an advanced course in quantum optic goes to open quantum systems. And these are the lectures at the moment that I offered. And
are these at bachelor or master level?
No, these are all the master courses. Since I have also this other field of research, which I'm equally pursuing, which is in the same category of analog optical computing. So I both pursue the quantum side, but also the classical side, which is using regular light, if you say. And this goes more in the direction of this neuromorphic computing. So essentially using analog classical optical computing, but for realizing physical systems that can do AI type calculation. More specifically, we're trying to realize optical neural networks. So neural networks that work with light. In this direction, I offered now a project, this Photonic neural network project, where you get to really learn the basics of how one designs these type of optical neural network, which are, you essentially try to apply machine learning based design approaches to realize an optical system, which, for example, can do something like image classification for you. But the information is coming with light, getting processed in the system with light, and then the output is also light, where you detect. And then you sort of extract some abstract information.
Interesting. And how are the accuracy of these systems compared to, let's say, a traditional neural network based on digital computing? Good
question, and topic of active research. I mean, that's again one of those things with light where the same type of advantages and disadvantage that you have for quantum photonic computing, you will encounter also for classical optical computing, where you could potentially have less energy consumption. You could potentially have much more energy, much more information processing capacity, but then you're also encountered with the problem of, light not interacting with light very efficiently, which means it's not easy to have what you have in regular neural networks, which are activation functions. For people who know more, you have sigmoid function when you try to train your neural network and these type of things, which are nonlinear functions, and these are hard to do with light. So that's also an active topic of research where I also pursue that, try to solve that problem. But if you come then to the Photonic Neural Network project, there at least we are working with linear optical systems, so just using linear diffraction and scattering of optical waves. If you have a fully linear system, then you're limited in the complexity of your neural network. If you now come to the Photonic Neural Network project, you will know what's the classification accuracy in percentage for handwritten digit recognition task.
Okay, I would encourage all the students then to go check it out. And do you also offer something for the bachelor level students as well?
Not at the moment. And as said, I mean, this is what I try to do now. I mean, I now have a little bit of experience from the feedback to, I guess, the courses that I'm getting. And I have to try to see what would really be in the best interest of also the students. And there seemed to be a lot of interest in this AI topic from the students. At least this is what I felt now. I would try to take that into consideration and try to see for the maybe not next semester immediately, but the one after, if I can come up with more interesting courses for our faculty.
And how can they reach you or your group, for example, your team?
You can email me, or you can come to my office and knock on the door. I mean, usually I prefer the emailing option.
I would also suggest that. If you say knocking on the door, then you might have a lot of students knocking on your door as well. But okay, so they can contact you by email, and you would be able to answer some questions as well. Then another question is for our prospective students who still are deciding whether electrical engineering is the right field for them. What advice would you have for them, for example, if they are interested in this field of quantum computing and photonic quantum computings? Is it because from the name it seems more physics, but is electrical engineering something that how that fits in, and whether that is the right field for them to pursue within this electrical engineering bachelor's or master's?
So the electrical engineering actually is one of these interesting topics. I mean, in there it's a very broad topic. I mean, in there you have many different specializations, and I would say you gain a type of expertise, which I mean also applied to me, that you can then move in various directions. You would gain, I mean, in electrical engineering, you also learn a lot of physics, especially Maxwell's equations, which is the whole foundation of photonics. You would also learn in electrical engineering, and you work a lot with it. From that aspect, then in electrical engineering, you can go in many different directions eventually, right? I mean, more like energy systems or power systems, in control systems, in robotics. You can go in the direction of optoelectronics, which is more like really close interaction between electronic and photonic systems, and you could also even move fully to the photonic side. So there are many different directions, probably some that I forgot. So I would say there you're sort of in an interesting spot that you can move in various different directions. Now, just specific about any type of photonic computing technology, quantum or neuromorphic, all these systems, or let's say it this way, for all these new generation of computational technologies, whatever they may be, even, for photonics at least I can say this very strongly, for them to become useful, they have to be in tight interaction with electrical/electronic systems. At the end of the day, if you want to have a functioning photonic quantum computer, there would be heavy use and involvement of electrical and electronic systems in it. So this is not like, because you need to input signals, you need to read signals, post-process, and sometimes you have hybrid type of components in there, like optoelectronic components, which sort of balance the things that light cannot do alone. Then you use optoelectronic system to help, so gain help from electronic system. And this is a very important, I would say, field of research. So you really need people with optoelectronics knowledge. So I would say, since anyway these type of new generation of computing systems must have involvement from electrical engineering to work, that opens an important place for electrical engineers, if they are interested in these technologies, these new photonic quantum computing technologies, to enter their field from their side of the expertise, right? I mean, maybe you have to learn a bit more photonics, maybe you have to learn a little bit more quantum, but then you take the responsibility for a very important part of these systems, which anyway is needed to realize these systems. So this is how I would see it.
Yeah, very important point. And I also believe that, for any advancement, you need to have interdisciplinary concepts. And in this case, photonics, physics, electrical engineering, and overlap of that through optics as well. And it's not just for this case, but in general as well. I mean, you need to have those interdisciplinary skills. And I also agree that electrical engineering offers you the variety of these skills that you can use in a lot of fields as well, also with AI and computers and more traditional concepts as well.
Yeah, I mean, there I want to add that in that aspect, in a sense, I would think Paderborn is also a very, very unique place or an interesting place for that, because, well, you have strong electrical engineering department here, and, well, there's a master program for this, but at the same time, there's a very strong, well, photonic community and physics community also, which are working on this quantum computing technologies. So there is very, very strong connections there in the Paderborn University, and also we have a strong computer science research at the Paderborn University, which addresses a lot of these algorithm aspect or software aspect or machine learning aspect. So let alone also other faculties like mechanical engineering, which covers different aspects. So, I mean, I would say as an electrical engineer, you're in Paderborn, you are at an interesting place where you can really have this opportunity for interdisciplinary contact and collaboration with all these different directions, which I think is, well, very interesting.
Okay, that's very, very interesting. I mean, that all those things that we talked about, and also for the students and also for me to know and got to know lots of new stuff about, photonic systems and quantum systems as well. Last but not the least, any common misconception about electrical engineering that you'd like to correct for our listeners?
Misconception, I don't know. all the things I know about electrical engineering are good things.
Okay, that's the way to go.
You tell me the misconception, I can correct it.
Well, I don't know. Are they always in the lab working with hardwares or?
Oh, not necessarily. I mean, there are a lot of, I would say, well, theory-oriented groups probably also in electrical engineering, but no, that's easy to correct. Not always. But you have the opportunity to be in the lab, I guess. I mean, there are different categories of lab. I mean, maybe my definition of lab is very different than robotics group definition of lab, or, well, a people working with energy systems, or but I would say at least in electrical engineering, there is a lot of opportunities for doing practical things. Well, maybe less with me, since I'm a bit more on the theoretical aspects of things, but overall you have a lot of opportunities to also, well, see things work, which I find very interesting, to see the fruits of your labor immediately.
Yeah, I think that was all my questions. I don't know if you have any closing comments or closing remarks that you'd like to say at the end, something that I might have missed.
I don't have a good statement, but I mean, I can tell you that, well, it's interesting. So maybe, I don't know. Well, okay, maybe I can say it this way. Maybe there could be a misconception from watching some TV shows that, well, maybe these engineering guys or these natural science guys, they're all sitting in their dark rooms and labs, and then, I don't know. And maybe they're not fun. And, well, I can tell you that at least that's not the case. There's life going on in this engineering faculties, and there's also fun going on. Then there's also interesting activities that is going on, and you will be really doing things at the forefront of not just science, but application for real life nowadays, because especially these electrical systems, I mean, they are in everything. They're in robots nowadays. They're in maybe automotive industry with self-driving cars. There are, well, electronic chips in well, your well, everything essentially. Also with the AI now, there is a lot of new machine learning topics coming into the electrical engineering community, and, well, also the more interesting, well, in the sense of fancier things like quantum technology. So there is a lot of interesting things happening in this electrical engineering community, really at the forefront of science, but also application in life. So you will be doing a lot of interesting things, no matter in the industry after your studies or in the academia. Well, it will be fun.
Great. That's a good way to conclude it. So yeah, it was a pleasure having you at
Thank you
this
very much.
podcast, and hope our listeners would enjoy it. And of course, there's always limited time, even though I would like to chat with you for more, and we could do it for multiple hours. But yeah, if you are more interested in having a part 2 of this podcast, then let us know, and we could continue this discussion as well. If you want to learn more about Professor Saravi and his research, check out the university website, and who knows, maybe soon you'll be working with photonic quantum systems yourself. Yeah, thanks for listening, and looking forward to see you guys in the next episode.
Current Affairs, the podcast of the Institute of Electrical Engineering, headed by Patricia Höfer at Paderborn University. Host Dr. Tanuj Hasija, organization and editing Yannick Grebe, narrator Yasemin Shenjan. If you like Current Affairs, please leave a review.